In Module 11, we will discuss the main structural adhesives.
So let's start now to describe the main structural adhesives. And let's start with the most important one, the epoxies. They are very strong, but they are very brittle. That's the main mechanical properties. They have a low shrinkage. That helps a lot because in a joint we don't want an adhesive that shrinks a lot during a cure, because this would introduce a lot of residual stresses. Typically, epoxies shrink by about 5% during hardening. They can be provided as one or two parts. What does it mean? One part, the resin and the hardener are premixed. Two parts, they are provided separately. You have the hardener and the resin separately. The cure is exothermic. That's a disadvantage because you would have a heating during cure, and if you use too much adhesive, you can also even have burning of the adhesive. That's why the adhesive makers, they limit in that case the adhesive thickness that you can use, and this is indicated in the data sheet of the adhesive. It can be limited, for example, to 1 millimeter. If you use more than that, you might have burning of the adhesive. They can be B-stage, that means they can be partially cured and be provided as film adhesives. I remind you that the adhesive is always applied in the liquid state. And if I say film adhesive, that's solid, doesn't make sense. It's not coherent with the fact that the adhesive is always applied in the liquid state. But when it's in the film, in the solid state, you apply the film and then you heat. And then the film will flow and will be liquid. And finally, it will harden. So even for a solid adhesive, it will go through that liquid state before it hardens. That's the main adhesive family of the epoxy. They are often cured with amines, especially those that cure at room temperature. And most are hybrid epoxy. That means they are modified with another polymer to improve the toughness. We have already seen that in the previous module, where thermosets are typically modified with rubber particles. For all the adhesives, you always have a scheme that shows the main positive points and the main disadvantages, all right? And here it's very clear, this strong man means that we have a very strong adhesive. Typical applications in the transport industry, for example, in airplanes, in fuselage panels, that's a very common application. Then the epoxies can be formulated with other polymers in addition to the rubber particles. They can be modified with polyurethane, and then we have a very, very tough adhesive. A typical application of this adhesive family is in cars for crash-resistant situations. They would be strong, and at the same time they would have a high ductility, which makes them very, very tough. If you want an epoxy that has to withstand high temperature, you can modify it with phenolic. Phenolics typically are adhesives that withstand very high temperatures. So, for example, if you need an epoxy that is to be used next to the engine or in another application where the temperatures will be at 150 degrees, for example, then you can use an epoxy phenolic adhesive. Then you have the polyurethanes. Polyurethanes, the key word is flexibility and deformability. They are so deformable, they are even called elastic adhesives. And you have of two kinds. You have the polyurethanes that are one part and the polyurethanes that are two part. And the ones that are really elastic are the ones that are one part. The two-part polyurethanes, they are still very deformable, but not as much as the one part. They would have a strength similar to epoxies, a bit lower, but a capacity to deform much higher. For you to have an idea of what it means to be elastic or to be rigid, I have here some specimens. And this is a one-part polyurethane, and you can see how I can bend it. It's very impressive. It's totally cured, okay, but very, very flexible. Another one in the form of a butt joint where I can flex very, very, very easily the specimen, all right? This is an elastic adhesive. To contrast with this, you have rigid adhesives like this one. This is a butt joint. I can't, of course, can't do anything. This is another one. I can't bend, impossible to bend. Here again, this is a cured adhesive. This one I can press very easily. It's very soft, whereas this one, it's an epoxy adhesive. It's extremely rigid. All right. Typical applications. One component, as I told you, the windscreens or the panels, the side panels in the buses. This adhesive cures by absorption of water, so it takes really long time to be fully cured. Typically 2-3 weeks to be fully cured up to the core. Of course, you can handle the joint after a few hours. That's what happens when you go to repair the windscreen of your car. But to be fully cured, because the absorption of water is very slow, it would take typically 2 or 3 weeks. The two components, they are more rigid, they are stronger, they are typically used for bonding composite materials. Better than epoxy adhesives in that case, because the epoxy adhesives are too stiff and they might cause delamination of the composite. With the two-part polyurethane, they are less stiff, they concentrate less the tension in the composite and they avoid that problem of delamination. Then you have the acrylics. And there are 3 kinds: the anaerobics, the cyanoacrylates, and the modified acrylics. They have all in common the fact that they cure really rapidly and they can bond many substrates. That's why they are used in fast assembly operations. The anaerobics, the origin of the word means that they cure with absence of oxygen. So typically they would be used to reinforce bolts. And the commercial name used is Loctite, all right? I have here an example of a Loctite adhesive, you see. The cyanoacrylates is the super glue that you use every day. I've shown you in the previous module an application of that super glue. And the modified acrylics is a kind of magic adhesive. That's adhesives that have the strength of an epoxy and also the ductility, but they can bond plastics typically without surface preparation. With an epoxy you would need surface preparation like plasma in case you bond a plastic. With these modified acrylics, the technical term is methyl methacrylate adhesive. You don't need any surface preparation. You could bond polyethylene, for example, without any problem. Then you have the phenolics. They are adhesives that are used when you need to withstand or high temperature. Typically they are cured with pressure because they cure by condensation. If you don't apply enough pressure, you might have a porous bond line. Typically they are used to bond wood because they are very cheap. But be careful, the mechanical properties are difficult because despite the fact that they are very strong, they are also very brittle. So in general, for structural applications, they would be modified. What's the thing about the condensation? Why adhesives that cure by condensation need pressure? That's because during that chemical reaction by condensation, there is a release of a water molecule, and because the cure is done at high temperature, the water would expand, it would be vapor, and this would provoke porosity in the adhesive. So to counteract that effect, you really need to apply a lot of pressure so that the vapor does not expand. That's why phenolics typically they really need high pressure. Epoxies, for example, they don't cure by condensation. They don't need a high pressure, just enough pressure to join the two components together. So a typical application of a phenolic wood constructions. And typical modifications of a phenolic, it could be with nitrile, for example, in the brakes of the cars. The brake pads are attached with nitrile phenolic. Vinyl phenolic are, for example, also used in electronic industry for the printed circuit boards to bond the copper to the plastic laminate. By the way, Redox 775 is an historical adhesive. It's a vinyl phenolic, and that's one of the first adhesives used in the aeronautical industry. And another case of modification is neoprene phenolic. Then you have the polyaromatics. That's adhesive really for very high temperature, even higher than with the phenolics. They can go up to 300 degrees C or more, and there are various kinds. The most important ones are the polyamide, the bismuthramide. They create a very strong 3D structure in the form of a ladder structure. And so, as I said, very high temperatures, but also extremely expensive and very difficult processing, because also they need pressure because they cure many of them by condensation. They are strong, it's true, but very brittle. Again, if you want to gain some ductility, you need to modify them. Typical application is for the supersonic aircraft, the fuselage. When they fly at Mach 2 or more, it would heat due to the friction with the air, and the temperature involved might be up to 200 or more, or next to the engines also very high temperature. So that's for the structural adhesives.